Hello everyone again. This is the last video of this week, and we are continuing on concepts of force, stress, deformation, and strain under the mechanical properties of materials. And in this video, we will be looking at deformation and strain. But if I were to remind you what's the force, what's the stress, let's look at the tensile stress that will be calculated whenever you have a cube, let's say a prismatic member, or at least if we are pulling this prismatic member from these two sides with a force F, you can calculate a tensile stress acting on any point within this cross section as the force divided by the cross-sectional area, and the unit is newtons divided by meter square. If the same prismatic member is this time applied to a force like this, which is not normal to that side, now this force will have two components, one normal and one shear, and because of this shearing force, we will be calculating a shear stress, Fs divided by the cross-sectional area. Note that for this member, subjected to this kind of a loading, we will have a normal stress as well, which can be found by the normal force divided by the cross-sectional area. So this is what we have seen before. And we have seen that the stress has units of newtons divided by meter square, or pascals, or most often megapascals as we use. Now, what's a deformation, what's a strain? Before we continue, we can say that all materials deform when subjected to some external loads. Like for this problem, we have a rod that's hanging down. If you were to pull this from this point A with a force P, this rod will elongate, so its original length L will increase by delta. And this delta is known as the deformation, in this case elongation. So deformation is the change in the dimension or the shape of a material. And we can have two different types of deformation. One is elongation or shortening type of a deformation, and these are observed under normal stresses. And we will also see another type of deformation under shear stresses. The material do not elongate, do not shorten, but rather distort. So it's called distortion. So what's a strain? Strain represents the deformation of a material per unit length. Like in this problem, the deformation is delta. If you were to divide this delta to the original length L, you will calculate a term strain. And the strain is, as you can see over here, is unitless. And just like stresses, we can have normal strains and shear strains. And if I were to explain like normal strain, let's say we have a material subjected to simple tension, and in this material the original length is L0 and the original width is, let's say, W0. If you were to pull this member, this material, with a simple tension test or uniaxial tension, this material will deform to this red dashed line form. And so it will elongate longitudinally along the load application, and it will shorten transverse to the load application. Therefore, we can calculate the elongation as delta, the final length LF minus L0 is the total elongation, and dividing that delta to the original length L0, we can calculate a longitudinal strain, and it is going to be a plus, indicating that this is a tensile strain. And in the transverse direction, shortening will take place, and that will be calculated as, let's say, delta, and which is WF minus W0. So WF minus W0. So you can immediately imagine that this is going to be a minus, and dividing that to the W0, you will be calculating an epsilon T, which is called transverse strain, and that minus sign indicates that it's a compressive strain. Now, for this structure, for this member, if you were to use a coordinate axis like this, XY coordinate system, you can immediately label this longitudinal strain as epsilon YY and the transverse strain as epsilon XX. The same problem. Now, this time, instead of simple tension, it is in simple compression, let's say. So the same problem. Now, we are not pulling it, but we are rather pushing it from these two sides. So, because of these normal stresses, again, we will have only normal strains, and those can be calculated very similar to what we have done. And the longitudinal strain will be calculated as delta, which is going to be a shortening this time, because the final length, the red one, is smaller than the original length, L0. So indicating that this is a longitudinal compressive strain. And this time, because we are applying compression, there will be some elongation in the transverse direction, and it can be calculated as delta WF minus W0. WF is larger than W0, therefore it's going to be a positive, and this indicates a transverse tensile strain. Similarly, if you were to use again a coordinate system XY, you can identify this as epsilon YY, the longitudinal strain, and the transverse strain as WXX. How about the shear strain? On a material subjected to simple shear, only one shear strain component will be observed. And what's pure shear? Well, in pure shear, as I have explained in the shear stress, we are applying from the top and bottom two equal but opposite stresses that are acting parallel to the surface. And because of this square will now distort to a different shape, and the amount of distortion, theta, can be calculated as delta x divided by y. And for small strains, for small deformations, delta x over y will be equal to tangent theta. And again, the shear strain, I can show you on that riveted plate connection. If you were to take this rivet out, again, you can calculate the shear stresses acting on that surface, like over here. It was 90 degrees. We are applying these shear stresses, and because of these shear stresses, it will distort. And now I can calculate the amount of shear strain as delta x over y. And remember, unlike stress, strain is always dimensionless. And this ends the concepts of force, stress, deformation, and strain part of this lecture. And in our next lecture, we will be looking at the elasticity.